Hi, welcome to the Unstable Fluid podcast, where he's Shrek and I'm Donkey.
What are you doing in my swamp?
I mean, it fits so well. How's it going, Thomas?
Not too bad. Could be better, could be worse. Kind of just average.
Yep, that's fair enough.
I mean, I sound less checked out than I did a couple episodes ago, so it's an improvement.
This is true. I'm impressed you're functional in this weather, to be honest.
Cardiff got some rain today.
Ooh, that's nice. We are coming to you from, at the time of recording, in the middle of the heat wave, so it's gross.
Yeah, I had to close the window over a little bit earlier because the fan was on, it just blew rainwater in my face.
It's like, you know when you go to the cinemas that tried to do the 4D experience?
Oh, yeah.
Is it that sort of vibe?
And that it's really kind of crap. Yeah.
Yeah, exactly.
Oh, I had a friend who went to like one of these like 4DX cinema experience things. He only went once because the first film that he went to go and see in 4DX was Christopher Nolan's Dunkirk.
Oh.
Which starts off with like a soldier like running through French streets under fire. You just get like blasts of air past you as you're sitting there. It was the most terrifying like 2 minutes of his life, which is the start of this film.
Oh, jeez, yeah. I can't imagine that being... I don't know what movie would lend itself to like 4D experience, except for Spy Kids 3D, which is then ironic, I suppose.
I don't know.
Not really the right vibe.
Depending on the level to which they take the 4D experience, I don't want to watch any of the movies that I like because most of them take place in the vacuum of space.
You get the added benefit of just not being able to breathe. What could possibly go wrong with that?
More than I normally can't breathe, yeah.
Yeah. Although, watching movies in zero gravity, that would be quite fun. Or low gravity, sorry. Am I allowed to say zero gravity?
I mean, okay, what we colloquially refer to as zero gravity as the idea of, like, say, like astronauts floating around in the space station is it's not that there's no gravity, it's just that they're in, like, free fall. Because that's all orbit really is it's just falling but moving fast sideways at the same time.
Yes.
It's like you're moving like past the Earth fast enough that as you fall towards it, you always miss.
That is way more stressful of a picture than like just like very relaxing hanging about in space vibes.
I mean, that's how it would feel.
Yeah.
You'd be hanging about relaxing, like, because you're not aware really of you're moving sideways other than that you're orbiting the Earth every like an hour and a half or something.
Is this like how if you take your velocity right now with respect to like off Earth, we're actually going really, really fast? Is that sort of vibe?
Yeah, we're going like something like 1,000 to a couple thousand miles an hour or something.
Anyway, how have things been since we recorded last, Thomas, which was so recently?
Yeah, it's been a pretty eventful, like, 2 and a bit months. Yeah, since the last one, I don't know if I had submitted the paper. No, I submitted in June. So, yeah, I submitted my first paper.
Woo!
I went to the National Astronomy meeting, which I've been banging on about for many episodes at this point.
Yep.
Which was good. Presented, chaired a session, was good fun.
Very nice. Did you find a designated extrovert? Or were you the designated extrovert?
I kind of became the designated extrovert.
I am not surprised in the slightest.
Yeah. I mean, yeah. To be fair, like of those of us that went from like who were PhD students at Cardiff, I was one of the more senior ones. A lot of the people that went were first years.
Okay, yeah. At which point you sort of get it like forced upon you a little bit, where like you are the more senior person in the room, so you sort of become the mother of the group or respective parent, depending on preference.
Fair. Yeah, kinda. I think also just because the conference was at Durham, and I'd like met quite a lot of the Durham people previously, because Durham has a lot of people that do the sort of thing that I do. So I've run into them at previous conferences. So I think I probably knew a few more people going in.
That's really cute. I have a really bad Durham joke for you.
I think I can already see where this is going, but go on.
What's the mascot of Durham?
I don't know.
It's the Pink Panther. Durham, 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 Durham. It entered my head and I couldn't not share it. I'm so sorry.
Yeah, fair.
What's Durham's favourite video game?
I don't know.
Mario Bros. Durham, Durham, Durham.
How many of these do you have?
I'm here all week.
What happened after that? I got my paper comments back as well.
Ooh. Okay,
So,
that's like respectable turnaround, especially over the summer.
Yeah, like it was, give or take a couple of days, like a month. Like they were on time. which is weird considering the summer and how long I know
Yeah.
other people have waited for their comments to come back.
Yeah, I mean, that typically means that the first people they contacted to be reviewers accepted, I think.
Yeah.
Because a lot of
Yeah.
the times with the delays, it's not like the reviews are really hard to write or there's like loads of them coming. It's that they've asked someone, gone, hey, can you be a reviewer? And that person has not replied or
Yeah.
said they can't. And it's like the hunt for reviewers that takes
Yeah.
up time. But that's exciting. So do you have like a reasonable turnaround on that, or is it super fast? Or
It's reasonable. I think I have until like late October. It's not going to take that long.
oh, nice.
I think they give us what, three months to respond to the.
I'm going to start submitting to your
Reviewers'
journals
comments.
because mine are all like, you have 2 weeks, go. And you can email them and be like, hello, can we have longer? Pretty, please. But
I think it may depend on like how they classify the revision,
okay.
because I think the journal that I submitted to, I think, can do minor, moderate, and major
Okay.
revisions. And my collaborators have looked at the report and said, this really looks like a minor revision to us, but they've categorized it as moderate, which has maybe given me more time, possibly because they know that I'm a PhD student.
Yeah, I mean, that's quite nice. I suppose for editing purposes, then it helps to know, like, okay, this one is probably coming in for the addition 2 journals time or something, depending on how regularly they post out. That's exciting.
Yeah, it's not too bad as a like set of comments. It's only one that's kind of tricky, and to be honest, the trickiest part about it is telling them no politely.
Yes, yeah. The please and thank yous to reviewers.
Anyway, what have you been up to the last couple of months?
Oh, God. Well, so this is the thing. It doesn't really feel like that much time has passed since we recorded episode 9, because I think at the end of that episode, you asked me what I was up to, and I was like 7 weeks of back-to-back travel. And it was actually 8 weeks, and I can't count. But it hasn't been that long since I've got back from all of that. So I have been everywhere. I have done all of the things.
How everywhere is everywhere?
So actually, like, not as much as my normal international travel. I have been to Italy, which is my only trip outside of the UK, which was quite nice. So that was for a summer school.
Bringing your carbon footprint down for this year.
We're trying. As it stands, I think I'm only leaving the UK twice this year, to my knowledge. But we'll see. But no, I've been traveling around the UK, mostly England and Wales, I think. I'm going to try and sneak a trip up to Scotland at some point, just because I can. And one day we'll get over to Northern Ireland, but who knows. But yeah, so I have conferenced and workshopped and summer schooled and retreated, and I just fled. I was at a retreat. I have visited family. I have done all of the things. And I was actually listening to the previous episode quite recently, and I was just in hysterics because I was so confident that I had sorted time management, and I was so wrong.
We were both really confident about that. I was similarly wrong.
I don't know which version of myself was there, but honestly, I was convinced, and I think I'm slowly getting that back of like, right, we work and then we break, and we don't feel guilty about having time off. And I wasn't wrong in that I do love conferencing, and every single thing that I'd been to, so like half of my trips have been very research heavy, and half of them have been like science communication, maths communication heavy, and I don't regret a single thing that I've done. There isn't any one thing I would have pulled out of my calendar, but I think doing everything.
Well, I imagine you probably would have pulled out the spilling tea all over everything.
Okay, like of the trips that I've done, I wouldn't regret anything. By the end of the 7 or 8 weeks, I was so dead that I made a few fatal errors. I'd probably get rid of that. My laptop is no longer with us.
Is it actually dead, or is it?
It is being repaired, and I'll get it back at some point, but I had to apologise to work. For context, don't put full bottles of iced tea in the bottom of your work bag and then shove your laptop really heavily on top of it and then wonder why nothing works and is all sticky. That's bad. Don't do that.
Funny that.
But no, I really enjoyed all of the things that I've done. I've met lots of very cool people doing very cool things, both in academia and in science communication. I've been to the Royal Institution in London. That was a bucket list
Very
thing.
nice.
I've been in their lecture theatre where they record the Christmas lectures.
Oh, with Faraday's desk.
Yes, yeah. Although so the start of day 1, they were like, right, they put the Faraday's desk in for the conference. And then they had to move it to do the demos and to do like the sessions that we were running in the room. And they were like, if anyone wants to take a photo with the desk, do it now before we like move it out of the way and put it somewhere safe. So people were like having photos on the desk and do it. It was really, really cute. I decided against doing it because I'm like, I would really like to have a photo with the desk if and when I ever get to do a talk there.
Yeah.
So that's my challenge to myself. That's now my bucket list item, is to do a talk in the Royal Institution so that I can have my photo. Because telling people I didn't take a photo because of my ego is that was the thing I did.
To be fair, like, yeah, it's a bit of a bucket list item. Like, I've watched way too many of those.
How cool would that be? Like, of the places, it was very surreal being in there. It was also bloody warm. It wasn't like peak heat wave, but oh dear God, stay away from London if you can, because it's toasty.
To be fair, I try to do that as a general rule.
I think that's fair enough. But yeah, so I am 2 weeks back from all of my travels at the minute, and I'm slowly finding my feet again with sort of research and regular scheduling, and like all the stuff that we said in last episode of like trying to bring exercising back in and like doing the non-research stuff and building my life back up again. Which has been really nice, but it would be nicer if it wasn't so bloody warm. Oh, something else that I've done that has made me incredibly happy is, so when I passed my Viva last year, a friend of mine did a call around of the people I was at uni with, and everyone like signed a card, which was very, very sweet. But they wrote me a letter,
right.
And then they had it was all signed at the back of that. And I have now framed that and put that behind my desk. Because I was in my feelings a bit when I came back from all of my travels about, my research and where I'm at with my role and like 1 year in and all this sort of, reflective-y stuff. And just having a letter from my friends be like, you're amazing and we love you, has made me really, really happy. So that's now pride of place behind my monitor.
Nice.
How cute is that?
That is really cute. That's actually something that we do in the Astro group in Cardiff when people actually do their Vivas, that we get like the really big like Moonpig cards.
Yeah.
Like, we get one of those and cover it with like photos and stuff, and then everyone signs it.
Yeah. It's so nice. I think going and finding all of the cards and notes from people. Like, I still have ones when I graduated undergrad, and like when I was going off to uni, the place I worked as like my Saturday job, they wrote me a little card, and I have that somewhere as well. So yeah, I in my get back to work thing, I've just put all of these notes reminding me that people think I'm pretty cool. It's just nice.
Speaking of things that are nice, shall we talk about some science, since we've actually both been doing that a bit for once rather than just traveling?
What? Yeah, go on. So I don't know how we start this topic off beyond the fact that I asked Thomas one of my classic questions, and we were like, let's do an episode about it so Thomas can answer me in a way that is both helpful for me and others. So Thomas, is space sticky?
Right. Okay. You want to elaborate on that slightly?
Okay. So
I thought you were just going to say no.
Not really. Go for it. Just riff. See what happens. No, I guess the question was sort of motivated by, we say that space is a fluid, or like space can be modeled with fluids, and y'all use fluid dynamics to like model space.
Yes. Literally everything I do every day is running hydrodynamical simulations, treating it as a fluid. Yes.
Yeah. So in that case, space must have properties that fluids have.
Yeah.
There must be things in common so that the models work across scales.
Yeah.
And one of the classic, iconic, if you will, fluid properties is viscosity.
How sticky the fluid is.
So is space viscous?
So, this is... Okay. Yes, but... I think is
the answer to every question I ask at this point, like so far, has been yes, but... Which is like the third rule of improv, is yes and, no but, yes but.
Yeah, something like that.
I did some improv training with Kate Holmes recently, and I'm like, I know all of the things. Yes, space is sticky, but.
Okay, I exist in like the part of space where we're primarily talking about gas. So gas, definitely a fluid. We agree, definitely a fluid.
Yeah, I'm with you on that
one. There are other things you can treat like a fluid, such as
cats,
stars, and cats, and big crowds. Like, you can model a lot of things with fluid equations, but gas, we agree, is a fluid. It very much obeys fluid properties. So you can model the gas in the universe, be that in like a galaxy disk or around a galaxy, like I look at, or like in disks around stars and black holes. You can model that with the full like Navier-Stokes equation that includes everything, including viscosity. I don't.
Well, rude.
So, okay, I will elaborate. So for listeners who are not as well versed in fluid dynamics, the Navier-Stokes is like the equation for fluids. It includes all of the things, includes like one of the terms in it involves like viscosity, how sticky the fluid is.
That is one of the terms, yes.
But space is very big, and there's a lot of stuff in space, but space is still incredibly big, and so space is generally speaking quite low density. And by quite low density, I mean like we're talking like maybe a few particles per square meter in certain environments. So in those sorts of environments, the environments that I work in, I work with the circumgalactic mediums, the gas around galaxies that is very hot and very low density. We kind of ignore it in the vast majority of cases. We assume that astrophysical gas is, for most intents and purposes, inviscid. We just kind of assume its viscosity is not important, particularly because I work in simulations, compared to, for example, numerical diffusion and viscosity and stuff that happens within the simulation that is beyond what we're trying to talk about today. Most of the time we can treat it largely as inviscid. There are obviously cases where that is not the case.
Yes.
Some of those are things like shocks. So when something comes like smashes into a load of gas and compresses it, massively heats it up. It can be important there. I think it can be important in like accretion disks around like black holes and stars. It can matter. So there are cases where yes, it being like viscosity does matter, and you should use at least that part of the Navier-Stokes as well as just the simple inviscid Euler equations. It's kind of it depends.
I think that's reasonable. I think that that's sort of the answer I was expecting, I think. So like within fluid modeling, it's not like, oh, everything is always viscous. We actually, the fact that we give name the Euler equations to the lack of viscosity set of Navier-Stokes equations, like we already agree that looking at things that don't have this viscosity effect is important and relevant.
Also way easier.
Also way easier for fluidsy reasons and for numerical reasons. I guess it was just the like, okay, so like gas randomly floating about in space, there's so few particles going on that like they're not affecting each other. But like...
Well, they're not affecting each other through viscosity. The viscosity is not the important part, essentially. It's more likely that they're just sort of bouncing off each other, sort of collisionally. And there are other more important processes like radiation from stars affecting it more than its own sort of self-interaction through viscosity. Because, like, custard is pretty viscous.
Basically, my question was, because, like, okay, so viscosity is the fluid's, like, effect on itself. So particles or molecules of the fluid affecting its other molecules and effect on the fluid. Essentially, given a small parcel of said fluid, how much stress or frictional force between two different layers of it, two different elements of it, it feels. So honey is a fantastic example of a very viscous fluid that people are familiar with because like it's really sticky to itself. If you try and pour it, it'll like pull it because it's the force of the parcel of honey lower down the parcel above is very strong, so it's like pulling itself downwards. Whereas water is really runny and like not very viscous. As soon as you stop pouring it, it will just like detach. It doesn't have that like string cheese effect going on. And I guess, like, the thing that I was wondering was, like, if you scaled out enough, because, like, bodies or stuff in space has, like, gravity effects. It's sort of similar.
Yeah.
So is it pulling on itself?
So it is pulling on itself through gravity, but it is pulling on itself through gravity, but I guess that's kind of different to, like, viscosity. Because things in space will like self-gravitate. So like if you have like a cloud of gas, like that thing will like if you get enough like a sort of dense enough clump of that, it will just sort of self-gravitate itself and just start collapsing down.
I mean, they're different units, which they're two different things, right?
Yeah.
Gravity is an acceleration. She says confidently.
Yeah.
Yeah. Look, if it goes anywhere near A-level physics, I get very confused. Yeah. Whereas viscosity is or we can do this, Pascal second, I think. It's like Newton seconds squared.
Something like that.
No, Newton seconds per meter
I don't
squared.
remember what the units.
They're all somewhere in one of my papers is the ruined SI units of all of these things. I knew them at a point in time.
Pascal seconds, yeah.
Yay!
Newton second per meter square.
Go me. I got that right. Okay, so we're assuming most of the time then the stuff that you're looking at is like not viscous.
Yeah.
Is space a superfluid?
How are we defining superfluid?
So a superfluid is a fluid with zero viscosity. So there's like, you have, most fluids will have a viscosity, even if that viscosity is like 10 to the minus 7. But like truly zero viscosity, like absolutely bog zero, is called superfluidity, which is something that typically happens at very, very low temperatures, or like, for example, like liquid helium is like a superfluid, or it's very, very close to a superfluid. It's this sort of like ideal far end, like opposite limit to something that's very, very viscous.
Okay. I guess in the most technical sense of the term, by assuming Euler equations, you kind of do assume that it's superfluid because you kind of just assume that viscosity doesn't matter.
Mm-hmm.
So mathematically, you kind of treat it in a similar way.
Mm-hmm.
But the behavior would be completely different.
Yeah.
Like again, because the other physical processes that matter more, like thermal processes matter more, and gravity matters more, and also just like the fact it's just hideously low density. So like, I guess technically because we just don't include it as a parameter in the equation.
Yeah.
Technically, but not physically.
That's fair. I suppose the kind
it probably has it will have a viscosity. It's just like so small it doesn't matter. It's not that like the term would be so close to zero it's not worth including it.
Yeah. I think the sort of two things are like, so when we look at sort of the energy conserved in a system, normally there's like a little bit of loss to overcome viscosity, and that will scale depending on like how much the things that you ignore affect the overall system. Whereas, yeah, this ideal is like there is no energy to overcome when the fluid moves against itself. Also, a quick Google tells me that it's an approach typically used in theoretical physics where a vacuum is viewed as a superfluid. So that's the ideal model, I guess.
Sure.
Which is cool. It's also used in quantum mechanics a lot. Everything's quantum. Yeah. That's what we've learned.
Everything is quantum. Preview for next episode.
I'm going to be honest, I'm slightly disappointed because I was kind of hoping that space would be very viscous so that I could then ask, is space Newtonian or non-Newtonian? Which is where I was going with all of this, of like, let's have that conversation. So...
Well, before we go anywhere near that, there are some cases where it does matter a little bit
Okay,
more.
tell me about those first.
So, the sort of the classic thing where viscosity does matter is in accretion disks.
Mm-hmm.
So, for anyone who has seen the movie Interstellar, the big disk around the black hole, that's what we're picturing here. For anyone who hasn't seen Interstellar...
Me.
An accretion disk is essentially so an accretion disk it's a disk of stuff around an object that is accreting that stuff. It's taking it in. It's that mass that's in the disk is becoming part of the object. So if it's around a black hole, it means that mass is falling into the black hole, never to be heard from again. If it's around like a protostar, a star that hasn't started like nuclear fusion yet, that gas is all falling onto the star and making it more massive, making it hotter.
For those curious about this, episode 8, Why is Space Flat? I make Thomas explain more about them as well. Yeah.
But just to give you sort of the main thing is that, it's a disk of stuff moving around an object. And viscosity does matter here because it is because viscosity is how the stuff actually falls onto the object.
Okay. So wait, so that's how it falls like into the middle.
Because as we covered in the episode on why is space flat, things get flat in space because angular momentum has to be conserved.
Mm-hmm.
So angular momentum is the tendency for the thing to spin, to orbit, and to keep moving in that sort of circular-ish motion. And if it wants to go further in, it's got to go faster.
Mm-hmm.
So if you wanted to actually fall onto the object and not just go incredibly fast around it, it's got to lose that energy. And the way that it loses that energy and moves some of its angular momentum out further in the disk, letting that bit of mass fall inwards, is through viscosity transferring that angular momentum.
Okay, so it's like the friction, and then it's slowing it down.
Yeah, it's essentially it's a shear flow between like a bit like a parcel of fluid moving at some radius r, and then another parcel of fluid moving right next to it at r plus a tiny little bit. It's that shear flow interaction between them and the viscosity giving the bit that's slightly further out a little bit more angular momentum from the bit that's further in, that lets the bit that's further in move further inwards and eventually end up as part of a star or a black hole or, I don't know, I guess technically planets can form that. I think that's one of the models for planet formation, is that happens there too.
Okay. That's really cool. I suppose that makes sense though, because you sort of directly tie it into like, that's a much denser area of space, right? Inside of an accretion disk. So the things near each other start to affect each other. Yeah.
So much so that, particularly around like a black hole, they sort of brush up against each other so much that they heat up to incredible temperatures. So when we say that like a supermassive black hole is accreting mass and has an accretion disk around it, and it's actively like bringing mass onto it, that's what we call an active galactic nucleus, or an AGN. And the particularly bright ones of those are known as quasars, or quasi-stellar objects, and they are the brightest things in the universe. So the accretion disk around the supermassive black hole can outshine its entire galaxy.
So don't look directly at them?
We're far enough away you can.
Okay.
But yeah, if you're kind of closer to it, don't, because there's a hell of a lot of X-rays there. But yeah, so that's like, that is where viscosity does genuinely matter in space. And depending on how you define in space, there are other places where it matters, like exoplanets. It absolutely matters for exoplanets. It matters for stars. It matters for that sort of thing.
Okay, you got my gotcha, because I was going to ask about magnetohydrodynamics.
I mean, you are aware of what my PhD is in,
yeah,
right?
Like nothing to do with it, but I think it's a really cool thing about space.
My PhD is MHD, the PhD.
Well, you're doing it wrong then. Where's the viscosity?
It's an inviscid fluid.
Boo.
For all intents and purposes. It's the Euler MHD equations.
Okay, well in that case, it's fine. I would have thought that would have mattered more. Okay, so non-Newtonian space. Yay or nay?
Okay, I can answer the question that you're actually asking, or I can give you the pedant's answer.
Give me the pedant's answer, because I just want to geek out about non-Newtonian fluids.
Okay, the pedant's answer is nothing to do with non-Newtonian fluids. My argument is more that Newtonian dynamics don't really apply to things in space, and Einstein general relativity makes more sense. But
fine.
Newton did a lot of stuff.
Yeah. His name's kind of everywhere. Can I just geek out about non-Newtonian fluids now?
To talk about the non-Newtonian fluid stuff, I am not aware of any in space, but by all means, have at it.
If we throw custard in space, then it's non-Newtonian fluids in space.
Then the space station gets in a bit of a mess.
They will have done experiments in space.
Yes, they will have.
But for those of the listeners that don't know what I'm on about, because this is one of my favourite fun things in fluid dynamics that I didn't study, or I didn't do in my PhD, but I really kind of wish, if I hadn't done bouncing droplets, non-Newtonian fluids or any sort of like, the term that I like using is complex fluids, but like things like magnetohydrodynamics or non-Newtonian fluids, things where the behaviors aren't always dictated as constants, sort of complicated systems like that. So normally under the same sort of temperature, state, behavior, most fluids that are Newtonian will have the same viscosity. Basically, the viscosity is sort of constant outside of like heating it up. Like if I heat up honey, it's going to get a bit runnier. In this weather, everything is going to get a bit less viscous because it's too blinking hot. I'm going to complain about it the entire episode.
For the listeners to appreciate just like the level of discomfort, like how warm is it inside for you right now?
In my office, it's 29.2 degrees Celsius. Yeah, I'm toasty.
Yeah, that's not great.
No. But yeah, so basically, irrespective of amount of stress, the response of the fluid is going to be the same. The amount of force applying or the amount of friction is going to be about the same. For a fluid to be non-Newtonian, that rule no longer applies. So depending on the amount of force applied or the amount of stress applied to the fluid, it's going to behave differently. And there's like two classical different ways that this can happen. One of them is when it's called a shear thickening fluid, which means as I shear it, as I apply a force to it, it's going to get more viscous. So it thickens, it becomes harder to push against. And then the contrast of that is shear thinning. So as I apply a force, it becomes runnier. And the sort of go-to examples of that are things like oobleck is your classic shear thickening fluid, which is mix cornstarch into water in some ratio. And if you hit it, it will act like a solid. And this is where the classic like running on custard, or like if you put it on a speaker and it sort of looks like what's that movie? Flubber.
To check if anyone had done this, I now actually have like a video of someone doing that whole like put oobleck on a speaker on the space station thing.
Have they done it?
Yeah, they've done
Send it me.
It looks weird.
I want to see.
We'll put this video in like the show notes. So if you want to watch it, like it'll be in the description on YouTube, it'll be in the show notes on whatever podcast platform you're using. But it looks weird.
It really is like Flubber.
Okay, so what you're saying is if I slap custard, it's gonna be hard.
Yeah, that's exactly what I'm saying. Is custard also has this property of if you apply a strong force to it, it's gonna react and sort of increase its
how
viscosity.
hard do I have to slap the custard so that it does that and I don't end up in a massive mess?
I don't think it's. I think it's the integral property of the custard that it means that will always end up in a mess. But I dare you to try and find out. Enjoy. That can only end well.
If I do it, I will film it.
Thank you.
From a distance with a slightly longer lens so my camera doesn't get covered in custard.
Yes. But yeah, so the shear thickening fluids, generally speaking, the more force that you apply to them, the more they act like solid. So the opposite case then of a shear thickening fluid is a shear thinning, which I said was when you apply an increasing stress to it or you apply more force to it, it then thins. And those are typically things like when you have a suspension of something in a thinner fluid. So ketchup is a wonderful example of a shear thinning fluid where, like, if I shake it, I apply a force to it, it's going to thin, which is what they sort of want you to do when you pour out ketchup from a bottle, or you struggle to pour out ketchup from a bottle, is if you apply a force to it, it's going to make it slightly more runny. And that is really like useful in terms of mechanical processes and like knowing when things are going to act like more like a lubricant under forcing stresses, which is a lot of what my research was in the sort of lubrication theory side of fluid dynamics. And I'm going to say all of this with a straight face so that you have to leave it in.
Okay, so why then, like, we're talking about non-Newtonian things, like some that do shear thinning and some that do shear thickening. Like, what is the thing that makes a fluid do one or the other? Like, why?
Basically, that you start getting into sort of material science of it's the individual properties of the fluid. So both of the classic examples are actually suspensions. And I mean, the honest answer is we're not sure, go away. But the assumed answer that I'm going to convince you, I think is true, is that it's typically because there's a suspension. So like if you think of like the shear thinning example, ketchup, nail polish, blood, that one doesn't fit with this example, but it's in there. It's essentially little particles suspended in some sort of solute, and then you have to shake it to get the particles to resuspend because they all settle. And what that sort of looks like is potentially it gets really thick and clumpy in certain areas and your density is different throughout the bottle. Again, not talking about blood in this example. But with ketchup and thing, you end up with this like really runny bit and then like a really thick bit. And the viscosity of the whole thing is sort of dominated by that dense region. The flip of that, the sheer thickening. Okay, so a cheeky check on Wikipedia, shout out Wikipedia, says that it's something to do with the intermolecular forces within the fluid itself. So basically, in the same way that a water droplet really close to a bath, the forces between the particles in the droplet and the bath, it's Van der Waals forces that take over and the thing coalesces. It's that, but inside of the full suspension. So one theory is that it is sort of stable in that way, and it's the intermolecular forces that sort of dominate, irrespective of the force being applied. Now, why? We'll go find a material scientist and ask them.
Sure. If there are any material scientists listening, send us an email, send us a message.
Yep.
Stuff is in the description of the show notes. We want to know why.
So the one other type of non-Newtonian fluid that I think is particularly cool, and I see a lot of people studying, and I nearly ended up looking at, are viscoelastic and viscoplastic fluids, which are essentially like solid until they're not.
Right. Okay. You have just described things that melt.
Okay, but it's not temperature that changes it from solid to liquid or changes it from a pseudo-solid state. It's stress. Which, again, is things that melt, and it's just my emotional state.
Relate.
But okay, so the classical example of one is a Bingham plastic, which is an example of a viscoplastic material, which essentially is basically solid until a high enough stress is applied, until a high enough force is applied, and then it starts to behave like a fluid. So it's sort of that shear thinning example, but instead of its rest state being fluid, it's sort of nearly solid. And my favorite...
You're describing an undergraduate.
Yeah. Basically, the reason that I like them is because I did a workshop in South America and Chile with a bunch of people that do like mining, and they have like a slurry, like a dam of all of the stuff that gets pulled up. And mudslides are a fantastic example of a Bingham plastic.
Okay.
Which is weird. So we were looking at like you have a big pile of like slurry or like mud essentially, and then it'll stay there until a big enough force applies, and then it suddenly starts to go. So sort of like an avalanche, but obviously avalanches there's more complicated stuff going on. But this is like it behaves like basically solid, and all those particles stay pretty stable, and then it starts moving, and then as a whole it starts to behave like a fluid. And the faster it goes and the more force is applied to that system, or the steeper the hill, the more like a fluid you can start modelling this mud. The more sort of relatable version of a Bingham plastic is toothpaste.
Okay.
So you know when you squeeze toothpaste, and it's always a bit of a nightmare if you're not paying attention, because it like nothing happens, and then suddenly it like... Maybe I'm just bad at brushing my teeth. You squeeze it and like nothing really happens, and then suddenly it'll come out, but it'll come out quite constant.
Yeah.
That is because you'll apply a high enough yield stress, or you pass that yield stress, and then it starts to behave like a liquid, but it'll behave like pretty constantly. Hopefully you're not squeezing the tube too hard. Whereas if I held the tube vertically downward and like had the opening, it's not going to fall out because it's solid. I'm not applying a strong enough force to get it to all expel. So... You know what my question's going to be? Is there space toothpaste?
Is there space toothpaste?
Yeah.
Maybe.
That's such the non-answer. I love it. So I guess like the one I could think of would be like I suppose you said we're not including like exoplanet studies, but if you had somewhere that had lots of like mudslides and volcanoes and all of the interesting geological features.
Yeah, I mean, it's an infinite universe. The chances are, is there another Earth-like planet out there somewhere? Probably. Will we find it?
Well...
I mean, yes. If you ask me, are there non-Newtonian fluids somewhere that isn't Earth? Yes, certainly.
Okay, well that answers my question then. Slightly unsatisfying, but I have a question.
Go for it.
Or do you remember the trend that went around a little while ago that was like, people think about the Roman Empire, or like self-identified men think about the Roman Empire like way too regularly?
Well, like on a daily basis.
Yeah. Do you think about the Roman Empire that much?
I mean, yes. However,
Uh-huh.
one of the mods on my Twitch channel has the literal username of Roman Consul.
To be fair, like, usernames are now so much names that I forget that the words that are in there are words.
I mean, I also play a lot of grand strategy games.
I was going to say, like, that would be more where I thought you were coming from with it.
So, in terms of do I think about the Roman Empire fairly frequently? Yes, but tangentially.
Okay. And then, so my second question was going to be, like, what would be the thing that you think about on, like, a near daily basis? Like, what is your Roman Empire?
Ooh, that's a good question. The cop-out answer is the circumgalactic medium, because that's a cop-out answer.
So I guess, like, my answer, not something that I think about a lot, but I could definitely talk about for way too long, which is definitely, like, not the right question that's being asked. But one I will go for is definitely Buffy the Vampire Slayer, and its, like, extended universe. Like,
okay.
I have watched that show so many times that, like, I would say near annual rewatch, I think, spread out.
Right, okay.
Yeah, I found it at 14 and I was obsessed. Like, it's got vampires, it's got witches, it's got lesbians. Like, what more do you need?
Fair?
Honestly,
Fair.
like, what's her name? Alison Hannigan. Okay, I really like it. I'm gonna pretend that came across sincere.
Okay, well, I mean, if we're going by that sort of definition of, like, just it can include sort of pop culture things, I mean, Star Trek is, like, probably the obvious one for me. Way too much Star Trek.
Yeah.
Actually, wait, hang on. We're recording this on a Thursday. Let's do Star Trek tonight.
Wait, which show is still going?
Strange New Worlds.
Fair. I like it. There's just too much.
It's like
there's so much Star Trek.
There is a lot of Star Trek.
I'm still on Deep Space Nine.
Oh, it is a good one. I've had many arguments with people about Deep Space Nine because a lot of people maintain that it is, like, the best Star Trek show, bar none. And my argument is that of the Star Trek TV shows, it is the best TV show, but it's not the best Star Trek TV show.
I'm confused as to how those two rankings don't match up.
Okay, I guess the metric to me is different. The reason I say that I think Deep Space Nine is better TV show, but not necessarily the best Star Trek TV show, is that I think comparing Deep Space Nine to other television shows, it is very good. But I don't think that I think it is fundamentally different from a lot of other Star Trek, because, at least my perception of Star Trek, because I think of it as a sort of, like, quite hopeful, optimistic view for the future, whereas Deep Space Nine is not.
Not that. Yeah. No, I think, okay, that's fair.
It adds a lot of complexity to the Star Trek universe. I think it's really good at that. But I don't watch a lot of Deep Space Nine and come away thinking, like, with that sort of, like, hopeful image of, like the utopian Star Trek future that you get from, like, Next Generation or Voyager or something like that.
No, I think that's fair enough.
This may just be proving that Star Trek is my Roman Empire.
I think you have, conclusively that is definitely the right thing for you. I think you've also made me, like, second guess whether or not I actually like Buffy that much. Because I cannot have this in-depth of a conversation about it. I'm like, it's good. Some vampires, people doing flips. Freaking Oz is in it. Oz is great. Yeah, I don't know what. I don't really think that often.
Thank you for listening all the way to the end of this episode of the Unstable Fluid podcast. If you'd like to let us know what you thought of it, then why don't you leave a comment on YouTube, or you can message us on Instagram at Unstable Fluid Podcast. You can also email us at unstablefluidpodcast@gmail.com with any questions you might have. If you enjoyed the podcast, please do share it with a friend, and we will see you in the next episode.